Okay, Eurocode 1. So we're on page 8 of our handout. And in terms of if you wanted to flick to the actual Eurocode, it's after a couple of green pages. Again, it starts with the national annex. So we've been looking at our loading, and then where we've been talking about these ultimate limit states in Eurocode 0, it's all repeated in Eurocode 1. So this is why you would be ignoring Eurocode 0. But it's important to talk about Eurocode 0. Yeah, before we get into the Eurocode, I'm just going to try and narrow down what loading is. So a lot of these pictures you've seen before and it seems obvious. I'm just trying to set the scene of all the things that you need to consider. You've got to consider every possible issue with regards to a structure. Just to give you an example, if you design a portal frame and you've got your pad foundations down there, a lot of times you just think, well, a foundation is to take the load coming down, and then in terms of the force that's coming down, divide that by the area and you get the stress that you can put in the concrete, and then you can work out the bearing capacity. However, when it's windy, you've got a UDL blowing against there, so the wind's blowing over the top. You've got a wake, so you've got an actual sucking action, which I guess would be drawn like that. Or if you open the door to your aircraft hangar, all the wind goes in, and so all your wind's inside pushing against the walls, and that's trying to lift your portal frame off the ground. So you find that a lot of times in terms of designing the foundations, you're trying to design it to make it big enough so that the whole thing doesn't fly away. So your load is not necessarily just going down. You need to consider the load coming down, but you also need to consider the loads pushing against and pushing up, and then the weight of the actual foundation to keep the thing on the ground. So where you've got a column there, you just put your column down, and the bolts that you've got are to try and make sure that you're keeping the column attached to the foundation. So there is a number of combinations of loads that you need to consider. In terms of our loads, we try and use known loads where we can get the information from. So if you buy yourself a cooker, you can probably see how heavy it is. Where we don't know, then we have to estimate. And because we're estimating, you tend to take the most conservative assumptions, and then we apply big factors of safety where it's estimated. Our dead loads, weight of the structure, everything that can't move, like our windows, are they dead load? Doors, dead load or live load? They stay there most of the time. So yeah, the dead load or permanent load. You got live load, so that's a train. And so people, you arriving and you leaving, that's a live load. You've got to make sure that your building is designed for the worst case scenario. Snow, so is snow a live load or a dead load? Yeah, it depends on where you are. There is variable, which what you would consider snow as in the UK, but if you lived somewhere in Europe where there's lots of snow, it's called a quasi-permanent. So it's not permanent, it's quasi-permanent. And there's a factor of safety that you apply for that. In terms of your load, is it kilonewtons? Like what you've got coming down? I know that some of you may struggle with this if you've done structural mechanics with me, but is it kilonewtons or kilonewtons per metre or kilonewton metre or kilonewton per metre squared per meter, or like all of these aren't making sense to me, or kilonewton per meter per meter. There's lots of different options, and when you get your loading, especially for your assignment, which we'll bring out next week, knowing in meter squared or meter or per meter will have a big effect on your final answer. With this image here, so if we were to design this joist or this beam, how much of the load acts on that beam? Well, it's in terms of this flooring. So this floor, it says that there's a UDL and it's kilonewtons per meter squared. So that's an area load. So if you've got an area load and how much of that is acting on that beam, you've got to take the area, figure out what the load is, and then apply that to that beam. So we've got, in terms of the span, it's from there to there. Half of this floor will be resting on that beam, half of it will be resting on this one. So you'll find that this distance here is the same as the span distance, and then that there is the length of the actual beam itself. So that would be our area for the load. If we had a roof structure, these are probably the more complicated ones that I came across when I was looking at buildings. But if we were to design the loading for the hip rafter, you all knew what a hip rafter was? So if this is our hip rafter, what does our loading diagram look like? Is it a UDL? Like what's resting on that beam, our hip rafter? There's a plan of it. There's our rafter. In terms of the loading from this roof, half of it is going to be resting on this wall, half of it is going to be resting on the ridge. But how much is going to be resting there? It's about you trying to work out how much is resting on that. Now you could split it down to exact like this, and then design the smallest beam as possible. If in doubt, just create a larger area so it's considering more load. In terms of our loading diagram, there's more load as you get towards the ridge itself. So you've got to take all the weight of the tiles, the felt, the battens into consideration. And the further you go up to the ridge, the more loading that it's taking. Or in terms of column design, you'll realise that in my notes there is some calcs on column design. I don't know whether Chandra uses them or not, but if you want to design a column to the Eurocode, just follow those. It's the latest guidance from Thomas Telford. If we design this column, how much loading would be resting on this mid column? In terms of this corner, this section here will be resting on there. But in terms of that one, you've got that area resting on this middle column. Or if we had 2 stories, you've got the area from each of the floors that are resting on those columns. You've also got the weight of the columns themselves that you need to consider. That's a little bit of background of what actions are. Let's look at Eurocode 1 and the things that you need to consider. Eurocode 1. Next week we'll get into Eurocode 2. It has a content page. Eurocode 1 is split into 4 parts. We'll be using part 1 only. Again, you can print up the whole thing, but there's a lot there. We do look at bridges, cranes, silos and tanks. When we actually, if what we look at, we're looking at part 1, and you'll find that we're mostly just in part 1.1 and 1.2. In one of your other modules, you'll be doing wind loads and possibly snow loads. I think it's in the project module that you'll be doing that. So the Eurocode itself splits actions into 3 different types. So we've got our permanent, that's your dead load, your variable, your live load, and accidental. We won't be covering accidental damage. You have to consider how have these applied throughout of a building. Again, these are just screen pictures from Calcrete software, which also covers some calc, so it's worth having a look at it. But these are our permanent loads, so we've got our walls, floors, beams, roof, everything that's there. Now, in terms of permanent loads, they're represented by G. So we've got our permanent loads are represented by G, and then we've got this K. When we do our structural mechanics workout, we've got all of our loads. They're all characteristic loads, so they're the actual loading. So if I weigh 9 stone, my GK would be 9 stone. Then I apply a factor of safety for being a liar, and where I will multiply it by 2, and I will have a design load of 18, which is what I would use to do my design. So you find that dead loads, permanent loads, are represented by G, and then you've got your K value. Now you'll find that in the Eurocodes that it is split by the superior and inferior, if you are able to distinguish between them. For this module, don't bother with the superior and inferior. We just have a dead load. We're just assuming that there's not a significant variation. So we've got the National Annex, Eurocode 1 itself, and then the Eurocode does have a few tables representing loading, but they're not exhaustive. There's not a lot there. So I've created a couple of pages of tables with the loading for the materials that we'll be referring to. So what have we got? So we've got bulk densities of soils. Let's jump across to concrete, because that's what we're working with. So we can see that that concrete plane, as in it's not reinforced, that's 24 kilonewtons per meter cubed. So that's our load. Now you could have kilograms per meter cubed, which is specific weight. And so the top one is a volume. So if we're designing a slab of concrete, so let's say that's a beam, and we've got a volume, what we can do is we can go to plain concrete, so it's 24 kilonewtons per meter cubed. So if we multiplied it by the volume, we'd get the total load in kilonewtons from that beam. Now, most beams have got reinforcement in it. When it has reinforcement in it, it's heavier. concrete with reinforcement in is 25. You'll find that for most of the examples that we'll do, you'll be using this 25. After that, we've got our variable loads or live loads. So that's the people, the stuff that you store. We won't be covering wind and snow in this module. You'll be doing it in another module. How do we look at imposed loads in the Eurocode 1? If you go to Eurocode 1, let's so we've got Eurocode 1 on page 21 of the Eurocode. So I've got EN 1991, so the 1 is the Eurocode 1. We're in part 1-1 and we're on page 21. So in terms of when you're doing your calcs, the reference would be EC1 table 6.1. So if we were to look at this room, our dead load is our ceiling, our windows, walls. Imposed loads, you've got the tables, you've got you, and all the other bits of rubbish that you leave. Please, when you leave, can you just take all of your rubbish with you? There's just bins just outside. Don't leave your cups and that on the table. But if we consider all of those in the Eurocode, we first go to table 6.1, look at category of use. So which category is this room? What do you reckon? C1. So we got an area where people may congregate, which is in a class here. Oh, where's the attendance register? And then we've got C1. If you're not sure how it's going to be used, just scan down, find the worst case. That's what you do. Just assume the worst case. Assume the worst case. So we're C1. We take that over into table 6.2. So C1.
Is it not C2 because it says areas with fixed seats? Yeah.
Are they fixed? Yep. Okay. Let's say they're fixed. Okay. Let's say it's C2 then, because it does feel like a church, doesn't it? You know. Feels like a cinema.
Like a mini IMAX.
Cheers. Is it that good? Yeah, ratings on IMDb. So we're C2, jump into table 6.2, go down to category C2. So what we have within this, we've got a small queue and a large queue. The small queue is the one that you'll mostly use. Your small queue is your UDL area load. So if we were designing this building, this room, we'd be using a UDL of 3 to 4 kilonewtons per meter squared. Where it's underlined, that's the recommended value. So you always use the recommended value. It's always worth. Unfortunately, you've got to scan through all of the text, have a bit of a read through, see if there's anything else that applies. So, it says where necessary, QK and capital QK should be increased in the design where, and it gives you all these different scenarios. This QK, it's in kilonewtons. That's a concentrated load. So let's say that we had all of these people here, and we would use our 4 kilonewtons per meter squared, and let's say that we were expecting a really, really heavy person or something really, really heavy, then and say it was going to be bang in the middle of the room, we could draw our beam. We'd have our 4 kilonewtons per meter squared, and we're expecting someone heavy in the middle of the room or something heavy. We could take the QK concentrated load is in between 2.5 and 7. That's what you find statistically. The recommended value is 4, but if we're just really not sure what's going to be in there, you could take that value of 7. Again, we're looking at characteristic loads. So far we've had our dead load, our permanent G. Next, we've got our Q, which is our live loads, our variable. Again, I've put K against it because that's our structural mechanics calcs. This is actual weight of what we know that we're working with. When we've got a material, and say we thought it was 35, we divide it by something so that it comes to something like 30, and that's what we design with. So we reduce the value. When it comes to loading, say that was 100, we will apply a factor of safety so that we increase it, and like say that it was 150. So when we have a material, we reduce it by the factor so that we don't rely upon its full strength. And then in terms of our loads that we'd be applying, you'd be multiplying them by a safety factor so that we don't use the 100. We'll be using like a much larger value than what we've actually calculated. Now there's those that we multiply by, and you'll find that there unfortunately are a lot of factors for live loads to consider. So we're on page 10 of the handout. What you'll find is for the live loads, you also have other factors of safety, not factors of safety, variations, depending upon the scenario. So in Eurocode 1, 631211, equation 6.2, so underneath your table 612, you should have this formula here. Now what that is of an example of a variation, is what's the chances that all of you, like let's say there's an explosion outside, everybody in this building would run to this side to look out the window. So what's the chances that everybody, all of the variable load is over here on every floor and loading up? This equation says highly unlikely. This is saying alpha n, which is a factor that you'll be multiplying by whatever your QK is. So once you took the weight of all of the people, depending upon the number of floors that you have, n, so you have 2 plus number of floors, take away 2, times by this phi naught divided by the number of floors. So when you're designing columns, you'll be multiplying by this value here in order to reduce the variable load on a particular element. Where do you get this phi value? The phi value is probably the only reason that you go to Eurocode 0. This is where you get your psi 0, psi 1, psi 2. Psi 2 is like sort of, I think that's mostly to do with snow, permanent snow in other countries. You'll mostly be using psi 0 and psi 1, and you'll see when to use it. They'll tell you which to use, psi 0 or psi 1, and then based upon the category, you just go down again and say we're designing for this building. Let's go for category C, congregation areas. So we'll be using a psi value. A lot of times the psi value you'll use is 0.7. We've got our characteristic loads. We want our design loads that we use to design our beam or columns. So you've got your characteristic loads or your FK. Multiply that by your factors of safety. Your gamma F gives you your design. So if you've got your permanent load, your G characteristic load times by your dead permanent factors of safety gives you design dead. Same as your variable multiplied by your variable factors gives you your design. But then you've got all of these, well, you might multiply by phi values and other variations. So these are all the formulas. There's 3 equations for working out the design values of actions. What you're meant to do is use all 3 and then choose the worst case. That's what you're supposed to do. So equation 610, which may be the one that you mainly use, which will give the worst case. So it says equation 610 says you've got to multiply your dead load by 1.35. Now this is our national annex. We say 1.35. It used to be 1.4 when it was the British standard. So that's a bit of a change from British standard to Eurocode. And then we multiply it by, and then we add our variable load, which is what we multiply by 1.5. That used to be 1.6 in the British standard. But notice that we've got these sort of unfavourable and favourable. So for a permanent action, this GK, you've got unfavourable and favourable. And then when it comes to the variable loads, you've got like your main variable load. So let's say that the variable load is snow, but then you might have another variable load which you could have as wind. So you might you might split your variable loads up, and they're both multiplied by 1.5, but this additional variable load you've got to multiply by phi naught and this QKI, and you've got to read through here, pick off all the values. Our example here, if it was a windy day and we were designing how much uplift is there going to be, if you had snow on top and you're looking at uplift, the wind's going to have more effect if there was no snow. So you might choose to ignore the snow when you're considering upwards, but when you're considering the force coming down through the column, through the foundations, and you think that's when you would add the snow and maybe remove the wind that would be pushing up. So you can play around with the loads to try and get the worst case scenario. Let's not leave this session without doing some calcs. So hopefully it might reach the back. If not, you're going to have to write this out. So we have a 3 metre high reinforced column, Exhibit A, supports 700 kilonewtons dead load and 300 kilonewtons imposed load. Now it's using the words characteristic, so that's the actual load. Calculate the ultimate limit design load if the column is 300 by 250 in cross section and the weight of the concrete is 25 kilonewtons per metre cubed. From the question, we've got our applied permanent load GK. So that's from the question. Our dead load is 700, and then you've got the dead load of the column itself. We're told that the concrete is 25 kilonewtons per metre cubed. So your mass is density times by volume. So to change that 25 kilonewtons per metre cubed, to change that into kilonewtons, we've got to multiply by the volume. The volume of the column is 3 metres times by the cross-sectional area. So that 3 times by 0.3 times by 0.25, that's your volume. Then we've got our imposed load. We're told that the imposed load is 300 kilonewtons. So we've got our characteristic loads. So we go to our Eurocode. we go to National Annex of 1. So on the reference, on the right hand side, if you put EC0, it's in table NA-A1.2B, and we're going to use equation 6.10. So you should be writing that on the left hand side of your calcs as the reference. We're told we've got 1.35 times by our dead, our GK, characteristic load. So we're not splitting in between the superior and inferior. We'll cover that next week, an example with that. So we've got 1.35 times by our GK, and then plus 1.5 times by our QK. So that's where you're getting that information from. So stick that reference there. If this was my assignment, that'll be -1 or 2 marks. So in terms of you do your calcs, you get marks for putting in information, show your workings out. You get marks for having the correct answer. But you definitely need to have references. Why have references? You do the calcs, you hand it to somebody else to do the checking. They want to know, where have you got all of this information from? Like in terms of then there'll be some obvious things like the weight of concrete. You know, you could, that 25 there, if it wasn't in the question, you would write in where you got your 25 from. You know, there's no reason why you couldn't write in, you know, in terms of your mass is density times by volume, and that the volume there is 0.3 times by 0.25 cross-sectional area times by the 3 meters. That gives you the volume. So, you know, add in all that you need to try and show the person who's going to be checking what you've done. Stick your reference in there. So the ultimate limit design load is our gamma G times by our dead load, or 1.35 we found from the table. Our dead load is these two added together, plus our imposed load, which is 300, times by 1.5, that's not 15. This gives us 1402.